Hey, welcome back, everybody. Okay, so to wrap this 9-1 up, it's time to start talking about some data distribution shapes and something called the normal distribution. Okay, so what we want to look at is just some of the terminology and then something called the empirical rule. And I've already got some notes started here, so these are things you definitely want to write down. Okay, some things you really want to know. All right, so I started talking about 9-1 is the normal distribution and the empirical rule. Okay, so in this first shape right here, this is called a skewed data set. This is also called skewed. It turns out this one is called positively skewed, and this one is negative. And this one is symmetric, but it's called normal. All right, so this is called a normal distribution because it's symmetric. Okay, all right. So when someone says normal distribution, you need to be thinking bell. That's when you've heard the bell curve, the bell-shaped curve. A lot of things in life and a lot of things in nature are distributed normally. Not everything. And I wouldn't even say most things, it turns out, if you really want to get down to it. But they tend to want to be distributed more normal than these big skewed ones. Now, we saw a skewed one when we saw that weather station distribution with respect to height and things like that. All right, so this is a definition you want to pause and write down. Your normal distribution is a symmetric bell-shaped curve defined with mean mu, and that's the variable we're going to use, and standard deviation sigma. Now this is something a little tricky to understand here. I'm going to talk about this in some detail in a second. The area under the curve represents the probability with a total area equal to 1. Now remember, probabilities have to sum to 1. If you're going to flip a coin, it's going to be heads or tails. We don't ever say it lands on the edge and all that mess. So if it's going to be heads or tails, we would say the probability of a heads is 1/2. The probability of a tails is 1/2. We know it's going to land on one or the other, so there's a 100% chance that it does that. So the sum of the probabilities would be 1. Now, if you'll go back and remember your basic definition of probability, you're talking about the number of favorable outcomes divided by the total number of outcomes. All right, now keep that in mind as we start looking at this distribution down here, okay? So this is what's called a normal curve. And what we've got marked off here are standard deviations, okay? So one standard deviation from the mean, this is the mean right here in the center. So everything wants to live around the center. Most of the items are living around the mean, all right, in this distribution. A standard deviation from the mean to the right, two standard deviations from the right, and 3. Okay, so what they've come up with here, and I know this has got to relate back to probability. If you think about these being this distribution being the population of something you're studying, in our case, all the elevations earlier, okay, and they weren't normally distributed, but if they had been, and somebody said, well, how many of them are 1,000 between 500 and 1,000 feet? If you knew how many were in there, you could give a probability of selected one. Because remember, probability is going to be really closely related to the population proportion, right? As we find a proportion of a population, we've also found, in a sense, a probability of selecting that proportion of the population. So the two things are tied together pretty nice. So, all right, so the area represents a probability, and it represents the proportion of a population. So in a normal distribution with mean, mu, and standard deviation, sigma, here's the empirical rule. Approximately 68.2% of the data falls within a standard deviation from the mean. Okay, so that would mean left 1 sigma and right 1 sigma. So inside here, these two, there would be 68.2%. Notice how we've marked it down here. And definitely draw these in your notes. You won't be sorry you did this. All right, so 1 sigma to the right gives me 34.1%, and a sigma to the left gives me 34.1%, because remember, we're symmetric here. I can fold this thing directly across the y-axis here at mu if it's in the coordinate plane. All right, now, if we go 2 sigmas out, in each direction. That's what they're talking about, 95.4%. So, well, to find these 13.6s right here, you'd really just take your 95.4, subtract the 68.2 from that, and then divide by 2 by your symmetry, and you could fill this out. And I encourage you to take a look at that and do it yourself, so you can kind of fill these out. I just know these videos get so long, so I went ahead and worked on some of that for you and put one in here for you so you could write it down. All right. All right, so what they're going to do is they're going to give us some information, and we're going to use the empirical rule to make predictions about probabilities and possibly the number of the proportion of the population that has a certain characteristic or a certain number of standard deviations from the mean. And you'll kind of see how those work. And I think what I'm going to do here is I think we need to get into examples 1 through 4, but I'm going to pause this thing and start a new video. We'll call this the introduction to the empirical rule, and I'll see you for examples 1 through 4 in the next video.